All right, 3Us, here we go. Today we're going to do another lesson. Oh, that's not how I wanted to do it. There we go. Today we're going to do another lesson to do with stoichiometry. Same thing we talked about yesterday. And don't worry, if this seems a little overwhelming, we're going to spend quite a bit of time talking about this and just going through it. But today is about an idea called the limiting reagent. And for this, hopefully you got the instruction and you took a couple of model kits with you to do this lesson, because I'm going to walk you through here something, and I hope that you'll actually build it. So in the first example, with the model kits, I'd like to build 3 hydrogen molecules and 4 oxygen molecules. Now the model kits, the hydrogen's either yellow or white, depending on which kit you're using. And so I'm going to draw yellow hydrogens. And remember that hydrogen gas is H2. So we're going to build 3 H2s. All right, good, just like that. So I'm going to draw that, but I want you to actually physically build it. And then oxygen gas, and we're going to build 4 of those, is an oxygen stuck to another oxygen. But we have to make a double bond with that. So we actually use 2 springs, and they should fit together like this. And what I want you to imagine is that we put these hydrogens and oxygens together and let them react. Well, hopefully you know that when we let hydrogen gas react with oxygen gas, they react to form liquid water. So take a minute and take these apart, and without giving yourself any new stuff, see how much water you can make for me. So go ahead and do that. And anything that's left over, just put to the side. So see how many waters can you make here. And hopefully, if all's gone right, which sometimes it does, you should have found that after you had made 3 waters, you would run out of stuff. So this will look less stupid once I've put the bonds in. So once you had built those 3 waters, you've run out of hydrogen, probably. And what you should have left is 2 whole oxygens and an oxygen all by itself, just like that. So if we had 3 hydrogens and 4 oxygens, we get 3 waters plus 2.5 oxygens left over. Okay. So we're going to make a note that oxygen's left over because all of the hydrogen has been used up. All right, and therefore, when a reaction occurs in the real world, it's like this example up here, where sometimes we just have too much of one reactant, or maybe you like to think of it as not enough of the other. We don't always have the perfect ratio that we need. But a reaction is going to stop occurring when any one of the reactants is used up completely, when it runs out. And whichever reactant runs out first, whichever one is entirely used up, is called the limiting reagent. I probably could have left you a bit more space to write that, sorry. But the limiting reagent. You can kind of think of this like building cars. If you owned a factory that built cars, if you had 20 steering wheels and only 20 wheels to go on the outside of the car and drive, well, you have enough steering wheels to make 20 cars, but every car has 4 wheels, so you only have enough outside wheels to make 5 cars. And you're going to have to stop building cars when you run out of wheels, even though you have steering wheels left. And this is the same idea. So we'll look at another example. If we have 3 carbon atoms, all right, we can use those to react with some hydrogen gas to make something called methane. All right, and normally it takes 1 carbon and 2 hydrogens to make methane. So here, we're going to come back and give ourselves some hydrogen, and we're going to imagine that we have 4 of them all together. And again, I'd like you to actually put this stuff in front of you using the model kits. And carry out the reaction and see what you get. So try using this to make as many carbons with 4 hydrogens stuck to them as possible. And when you do that, what you should see, hopefully you've paused this video and done it, is that if you put a carbon in the middle, and then it's kind of got, I'm going to try to show this sort of 3D shape to it, but it'll kind of have one coming at you like this, another one kind of going backwards like that. And it should make that little tripod shape. We call that a tetrahedron. You'll learn all about that in grade 12 chemistry. But you should be able to build that, and you should actually be able to build 2 of them. You should have enough of everything to build a second one. Oh. Hello, come here. And there they are. Make that a touch. Oh, make both those just a little bit smaller. There we go. I like that. All right, and when you do that, you're still going to have a leftover carbon. Right? And the note we're going to make about that then is just to say that hydrogen was the limiting reagent. It's the thing that ran out. All right, well, with that in mind, we're going to go through and look at a few questions like this. And we want to first look at just a nice single displacement reaction. So here we have a reaction where 3.2 grams of magnesium metal is added to a beaker that has 5.3 grams of copper 1 chloride. And they're asking, how many grams of solid copper do we get? So the first thing we need is a reaction. And so we look, we have magnesium metal, so Mg, that's a solid metal, is going to react with copper chloride, that's aqueous. Right, and it's copper 1 chloride. So if I wanted to crisscross that, I'd come up here and I'd say Cu with a charge of +1, Cl with a charge of -1, gives us CuCl, just like that. And when I crisscross that, I will get copper all by itself. And now, magnesium with its 2+ charge is going to end up with chlorine with its -1 charge. And when you do that, you'll get MgCl2. just like that. I'm hoping that feels pretty comfortable to you guys now. But the first thing we need is that chemical equation. All right, this is just like your single displacement lab that we did, where you made an activity series. And now we need to balance this. And if we look over here, we have 2 Cl's. So I'm going to have to put 2 here. And that means now that I'm going to need 2 coppers. So there's our balanced chemical equation. Now, the thing you have to notice when we look at this question is that we've been given 2 pieces of information. We know that we have 3.2 grams of magnesium, and we know that we have 5.3 grams of copper 1 chloride. Now, we always tell you to answer these questions by starting with the given. Well, here we have 2 given, and so the answer to that, or the solution to that, is to answer the question twice. All right, and we're going to do some stoichiometry just like we did yesterday. So we'll start with this given, that we have 3.2 grams of magnesium. Right, and if you remember, we always said that the first thing we need to do is figure out the molar mass of everything. So I usually like to put a little section aside down here and figure out the molar masses. The molar mass of magnesium, we just have to look on the periodic table. All right, and when I look at the periodic table, I see that magnesium has a mass of 24.31 grams per mole. And then we also have to know the molar mass of copper chloride. All right, and again, we're going to look at the periodic table here. All right, and oh, geez, what did I do there? It's going to be the molar mass of copper plus the molar mass of chlorine. The molar mass of copper is 63.55 grams per mole. And the molar mass of chlorine is 35.45. When we do that, we should get 99.0 grams per mole. And we need the molar mass of magnesium. Nope, that's not true. We already have that. And we need the molar mass of copper. And the molar mass of copper is 63.55 grams per mole. All right, we're going to have to use all 3 of those in answering this question. And so it's the first thing we should do. Once we've done that, we're going to go back and just start answering our question. And we said we're going to start with the fact that we have 3.2 grams of magnesium, because that's the first thing they've told us. And we're going to say, okay, well, if we have 3.2 grams of magnesium, I don't want to know how many grams of magnesium I have. I want to know how many moles of magnesium I have. And then so we come back down here and look, and we say that 1 mole of magnesium has a mass of 24.31. All right, and that just comes from here. And if I were to stop calculating now, I would know how many moles of magnesium I had. But the question doesn't ask that. It asks how many grams of solid copper. Now again, I can't go from grams of one thing, or from moles of one thing to grams of another. So I have to cancel moles of magnesium. And if it's copper I'm interested in, I have to go first to moles of copper. And these numbers are just going to come directly from the balanced chemical equation. And if we look in the chemical equation, there's just 1 mole of magnesium. So that goes down here. And for every 1 mole of magnesium, we get 2 moles of copper. We put that number there. And again, now moles of magnesium cancels with moles of magnesium. If I were to stop calculating now, I would know exactly how many moles of copper will be produced. But we don't want to stop there. The last step is to cancel moles of copper and find out how many grams of copper we have. And this is where we look down here. We see that each mole of copper weighs 63.55. And so we put that number in here. We say there's 63.55 grams of copper in 1 mole. Try that again. All right. And now I'm just going to ask that you put that into your calculator. And when you do, you should see that the answer is 17 grams of copper. Now, this means that if we used up all of the magnesium, we would get 17 grams of copper. But the other thing I have is 5.3 grams of copper 1 chloride. And it could well be that that's the limiting reagent. It could be that that runs out first. And if that's the case, then we will get a different answer. So we are going to do the question again. And this is why I said you answer the question twice. Because we're now going to say, okay, what about this given? Well, if we use all of the copper chloride, we begin by saying we have 5.3 grams of copper chloride. And just like before, we're going to cancel grams of copper chloride and determine how many moles of copper chloride we have. And we've already done that calculation, and we know that 1 mole of copper chloride weighs 99.0 grams. And this information comes directly from here. And if I were to stop calculating, oh, that could have been bad. And if I were to stop calculating now, I would know how many moles of copper chloride I had. But we don't want to stop calculating now because we don't want to know anything about copper chloride. The question, of course, asks for solid copper. So we're going to cancel moles of copper chloride and determine how many moles of pure copper we have. And again, we just look at the balanced chemical equation. And if we look at the balanced chemical equation, we use 2 moles of copper chloride in this reaction, and we produce 2 moles of copper. And then, just as before, if I were to stop calculating now, moles of copper chloride would cancel, and I would know exactly how many moles of copper I have. Of course, I don't want to know how many moles of copper I have. I want to know the mass of copper. So we're going to put moles of copper on the bottom to cancel it. And we're going to put grams of copper on the top, because that's what we want. And again, we just come down and look at this information here, and we see that there's 63.55 grams of copper in every 1 mole of copper. And go ahead and punch that into your calculator. And when you do that, you should see that we only get 3.4 grams of copper if we use up all of the copper chloride. So, if we use up all the magnesium, we'd be able to get 17 grams of copper. But if we use up all of the copper chloride, we're only able to get 3.4 grams of copper. So the last step is to pick the most appropriate answer. And if we look, we take the lowest value, always. And we're going to take the lowest value because that means that that compound that we started with in that given, in this case 5.3 grams of copper chloride, ran out first. So we would be able to say, therefore, copper chloride runs out first. And we call that the limiting reagent. And we'd also be able to say, therefore, 3.4 grams of copper are produced. Okay, and I want to look at one more example, and then I'll send you on your merry way to do some homework. All right, we're going to do a double displacement reaction this time. This time we're going to have calcium nitrate reacting with sodium carbonate. So calcium nitrate, calcium has a charge of 2 plus. Nitrate is NO3 with a charge of -1, and so we get CaNO3 2. Okay, and then sodium carbonate, Na has a charge of +1, carbonate has a charge of -2, so we get Na2CO3 when we crisscross them. All right, so now let's just write our balanced chemical equation. Calcium nitrate reacts with sodium carbonate. And when these react, they're going to switch partners, right? It's a double displacement reaction. And so we're going to end up with sodium nitrate and calcium carbonate. Just like that. It's a little squished for my liking. All right. And then we have to balance it. And if we look at this, we would say, okay, well, over here, we have 2 sodiums and 2 nitrates. So I have to put a 2 there. And that should leave everything balanced, because over here we have 1 carbon and 1 carbonate, and that's what we have here. So there is our balanced chemical equation. And now again, in the rare case where they tell us that we have a certain amount of calcium nitrate and a certain amount of sodium carbonate, we have to answer the question twice. Right? And they're asking us how much calcium carbonate will form in grams. So we're going to need to know molar masses of all 3 of those things. Right? And that kind of stinks. That's the nature of it. But we're going to need to know the molar mass of this, the molar mass of this, and the molar mass of this guy. Now, in the interest of full disclosure, you can absolutely calculate them. I expect you to be able to calculate them. But in a case like this, I'm just going to ask Google. What's the molar mass of calcium nitrate? What's the molar mass of sodium carbonate? What's the molar mass of calcium carbonate? There we go. And again, there's no reason you can't figure those out using a periodic table, but it's not really what this assignment's about. So I'm happy to just look those up at this point and write them down. But what we have to absolutely do now is work our way through the question. And we have to work through it twice because we've been given two pieces of information. And we have to see which one of these is going to run out. So the first thing that could potentially run out is that we start with 4.5 times 10 to the negative 3 grams of calcium nitrate. And I'm just going to shorten that to be CN, because otherwise I feel like I might go crazy. And we're just going to work our way out here. And we're going to say, okay, we don't want to know how many grams of calcium nitrate we have. We want to know how many moles of it we have. So from this number, we know that 1 mole of calcium nitrate weighs 164.1 grams. And if I were to stop calculating right now, I would know how many moles of calcium nitrate were used in this reaction. But we're not going to stop calculating right now because we don't want to know anything about calcium nitrate. Remember, the question asks about calcium carbonate. So we're going to cancel moles of calcium nitrate, and we want to know how many moles calcium carbonate. And so we just look to the balanced chemical equation. We have 1 mole here, and 1 mole here. So 1 mole of each is in this reaction. And again, if I were to stop calculating now I would know how many moles of calcium carbonate I have, but I don't want to know moles of calcium carbonate. I want to know grams of calcium carbonate. And again, for that, we're just going to look to the molar mass. The molar mass of calcium carbonate is 100.1. There's 100.1 grams in each mole. And now if I stop calculating, I should know how many grams of calcium carbonate are produced. So go ahead and punch this into your calculator, see what you get. All right, so I'm going to say 4.5 times 10 to the negative 3 times 1 divided by 164.1 times 1 divided by 1 times 100.1 divided by 1. And when I do that calculation, I get 2.7 times 10 to the negative 3, all right? Or if I prefer to think of it that way, 0.0027 grams of calcium carbonate. All right, but with every one of these questions, we need to try doing them twice because we have 2 sets of given. So we have to try this whole calculation again, this time using the sodium carbonate we're given. And so we're just going to set it up again. 3.4 times 10 to the negative 2 grams of sodium carbonate. And we're going to follow the exact same steps, which is that we want to know at first how many moles we have, not how many grams we have. And we're just going to look at the molar mass and know that 1 mole of sodium carbonate weighs 106.0 grams. And if I were to stop calculating right now, I would know how many moles of sodium carbonate I had. But that's not what I want to know. Because again, the question really asks about calcium carbonate. So we're going to cancel out moles of sodium carbonate and figure out how many moles of calcium carbonate we have. And if we look again at the equation, you'll see we use 1 mole of sodium carbonate in this reaction, and we produce 1 mole of calcium carbonate. So it's a 1-to-1 stoichiometric ratio. And as always, if I were to stop calculating now, I would now know how many moles of calcium carbonate we have, which is getting very close to the final answer. But the question is, how much of it do we have in grams? We need to cancel moles of calcium carbonate and figure out how many grams of calcium carbonate we have. No reason to put that so far to the left, because it's just going to make my life unpleasant when I go to write it in. And again, the molar mass of calcium carbonate is 100.1 grams in 1 mole. And so again, we're just going to do this calculation. 3.4 times 10 to the negative 2 times 1, divided by 106.0 times 1 divided by 1 times 100.1 divided by 1. And when we do all of that math, we now get 3.2 times 10 to the negative 2 grams. Or if you prefer, 0.0321. All right, and again, we go with the lower answer because, just like above, when we come back to those examples we did right at the beginning of the class, here, even though I had enough carbon to make 3 methanes, I only had enough hydrogen to make 2, so I can only make 2, and I just have leftover carbon. In this example, we had enough calcium nitrate to make 0.0027 grams. We had enough sodium carbonate to make 0.0321 grams, way more, 10 times as much. So we're going to use up all of that calcium nitrate. We're only going to make that much. And then all of that extra sodium carbonate will just be left over. When this question's all said and done, there's 2 things we can know. Therefore, calcium nitrate runs out. We call that the limiting reagent. And we go with the lower number, so 0.0027 grams of CaCO3 will be produced. All right, and you could even, if you wanted to, say that there is sodium carbonate left over. All right, so again, I'm sure this seems a little confusing right now, but I hope it made some kind of sense. I'm going to give you some practice homework, questions on here. And I think with a bit of practice, it should come along. So good luck, and I'll see you all tomorrow where we can take up this homework and really go through this stuff.